said, hey, you, let's do some DiffEQ. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DiffEQs. In this video, we will talk about slope fields, how to graph solutions through slope fields, and how to identify whether certain slope fields match up with particular differential equations. The types of differential equations we'll be working with are first order and of the form dy over dx is equal to some function of x and y. It may depend just on x, just on y, on both, or it may be a constant function. The topic is slope fields, and we can see how that name applies to this differential equation. On the left-hand side, we have a dy over dx, which is a slope, a change in y over change in x. And the field comes from the fact that at either every point in the xy plane, or nearly every point, depending on this function f, we have a slope defined. Now, what we'll be graphing today are partial slope fields. We can't actually graph a slope at every single point in the xy plane because it would be too cluttered. However, that doesn't mean there isn't a slope at every single point. There is, so long as that point is in the domain of this function. Here is a slope field that I've graphed by hand. Now, we will not be graphing slope fields for the following types of differential equations. The first is differential equations that are of the first order, but not exactly of this form. An example would be an equation like this. Another type of differential equation that we won't graph slope fields for are higher order differential equations. An example of this might be a second order differential equation, as we've written here. Now let's look at our first example where we actually start to graph a slope field, and you can see how I might have come up with something like this. For our first example, let's have the differential equation dy over dx is equal to x times y. If we want to graph this slope field, we'll want to pick certain points and then compute the slope there. Let's create a table. Here's a table with a certain number of points selected and their slopes computed. Notice, for instance, at the origin, we have 0 for x and 0 for y. This slope field tells us to get the slope dy dx, we multiply x times y. Multiplying 0 times 0 gives us 0. In the same way, for these orange and red points, 0, 1 and 1, 0, multiplying 0 times 1 and 1 times 0 will both give us 0. So at these 3 points, we all have the same slope of 0. In a similar way, if we consider a point such as 1, 1, this point in magenta, 1 times 1 is 1, so we have a slope of 1. For the purple point, we have an x value of 1, a y value of 2, multiplying 1 by 2 gives us 2. And again, that comes from this formula here. Now let's go ahead and graph these slopes to see what this would look like. Here we've drawn in all the slopes for the points we computed. Now let's fill out the slope field a little bit more by plotting some more slopes. Here's the slope field that's been filled in a little bit more. Now let's take a look at how a computer would fill this in. Here you can see the computer has drawn lines with arrowheads. Now's a good time to talk about the difference between a slope field and a vector field. Here are 3 different fields. The first 2 are slope or direction fields. You'll notice that the one on the far left has no arrowheads. The one in the middle has arrowheads. These are both what are called slope or direction fields. Compare that to a vector field. What is the difference between the two? In the case of a direction field or a slope field, the arrowheads will always point to the right. These can be left off, shown as just small dashes like so, because we know the arrows will always point to the right. On the other hand, if we look at a vector field, we have arrows that can point to the left. Besides the direction in which the arrows point, there's also a difference in magnitude. As much as possible by hand, I've tried to draw these dashes so that they're roughly equal in length. And again, very approximate because it's done by hand. In a vector field, the arrows may have different magnitudes. The thickness of the arrows I've drawn here is just to emphasize the fact that some are larger, corresponding to larger forces that would act on a particle or some object. The arrow down here you can think of as less force than the arrow up here. So both are pointing in the same direction, this arrow and this one. The difference is that the larger arrow exerts more force. Slope fields are nice because they tell us about the solutions of a differential equation in a way where we might not be able to otherwise understand the solutions. So let's go ahead and look at how solutions interact with slope fields. So solution y which should be highlighted in yellow, that's the solution to this differential equation, is such that if you take the derivative of y with respect to x, that is this highlighted yellow y, we get this function, which is here saying nothing more than exactly this differential equation. And it's such that at each point xy in the xy plane, where you have both y and f being defined. Graphically, it looks like so. We have a solution curve here, where in the slope field, all the slopes are 0. A line that has all slopes 0 is simply a constant line. Alternatively, we have down here a line that is not horizontal. At this point in particular, we have an instance where the slope of the slope field should be the same as the slope of the tangent curve to the solution. If I highlight the slope field below it, we can see that the slope field aligns with the tangent line to this curve at that point. Now let's talk about a concept known as isoclines. This will help us both graph slope fields more easily and identify them in relation to certain differential equations. So an isocline of a slope field is a curve along which all the slopes are the same. Suppose we have this differential equation, dy over dx is equal to 3x plus y. Now the slope is highlighted in blue to correspond to the slopes we've seen in blue in past slope fields so far in this video, to help reinforce that the dy over dx is the slope part of this, and that is given by this formula. Now let's say we want to look for the curves or isoclines where we have a slope of 0. If we recall that dy dx is equal to 3x plus y for this particular differential equation, it follows that dy over dx is equal to 3x plus y, and therefore we have 0 is equal to 3x plus y, since dy dx is equal to 0, and a slight rearrangement gives us that y is equal to negative 3x. Now if we graph this in the xy plane, this isocline, y equals negative 3x, we have this line here. And now notice this isocline, which we've highlighted yellow, is only there to tell us that everywhere along that line we have a 0 slope. So let us graph 0 slopes along that line, like so. Now this could have been done with any value besides 0, but 0 is a particular nice value to start with, not only because calculations tend to be easier, because it immediately tells you a lot about the slope field. In particular, when you're looking for the isocline, where dy dx is equal to 0, we call that the nullcline. So a nullcline is a special case of an isocline, and that's just where dy dx is equal to 0. Now let's look at an example where we plot with isoclines. Now we have the differential equation, dy over dx is equal to x squared minus y. It fits the form where we can plot a slope field. And now let's consider some isoclines. Here we've started with the nullcline, giving us this function. Then we get isocline A, where the slope should all be equal to 1, giving us this function or curve. And then we have isocline B, corresponding to slopes of negative 1, giving us this function. Now if we graph these three curves, we get the following. Now again, these curves are really there just to help us plot slopes. Here we've drawn the slopes and erased the nullcline line. Now let's do the same for the other two lines, keeping in mind that a slope of negative 1 corresponds to this function. And finally, we'll graph the slopes with a slope of 1. Now that we've gotten a sense of how we might graph this by hand, let's go ahead and look at a computer-generated image. Again, note that the arrows in this image are all going to the right, and slope field or direction fields will sometimes be shown with arrows and sometimes without. Also notice that the lengths of each arrow are the same. Now let's look at our last example, where we'll try to match a differential equation to a slope field. Here we have three different computer-generated slope fields. Let's say we want to consider the differential equation dy dx is equal to sine of y, and how that might correspond to one of these three slope fields. In order to do so, we might start by identifying some isoclines, and the best isocline to start with is the set of nullclines. There may be more than one. The nullclines occur where 0 is equal to sine of y, that is where y is equal to n pi, where n is some integer. For the scale of these three graphs, that will happen at three places: when y is equal to 0, when y is equal to negative pi, and when y is equal to pi. If we overlay these three isoclines, we can draw them as horizontal lines because that's where the slopes will be 0. Now we can see for the slope field on the left, at this point, the slope should be 0 if it's going to correspond to this differential equation. However, it's positive in the slope field. That means it can't correspond to this differential equation. Likewise, on the slope field on the right, if we look at this point in particular, the slope field has a positive slope, but if it's going to correspond to this differential equation, it should have a zero slope. We see that the middle graph at least corresponds everywhere to where the slope field should be zero. Here, here, and here. With a little bit more investigation, one will find that in fact, the middle slope field does correspond to this differential equation. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.